Good morning, mathematicians. Oh, did I? I did. I'm not going to hang out that long today because, whoa. I'm doing dangerous stuff there. So I got stuff to do. I got places to be. And so today's going to be short, like 20 minutes short, probably. Don't get mad at me. Well, whatever, you can do what you want, live your life. You're your own person. Unless you only exist in my head. Which, I mean, you only exist on the screen, so not even that vivid of a hallucination. Yeah. Can't trust it. Okay. Differential graded algebra is a graded algebra with a linear mapping, which is a derivation. And, okay. We don't need it to respect the grading? Oh, degree 1. Yes, so we do need it to increase the grading. You exist in my head? Oh, okay. That doesn't mean that you don't exist in the real world, of course. Okay, so a differential bi-graded algebra is just the same thing, but with a bi-grading. And it increases the total degree. And we've got a more flip-de-doop-de-doo going on here. Sure. An example of a differential bi-graded algebra can be constructed from two differential graded algebras by taking their tensor product and this flip-de-doo boy. Notice all the differentials in a spectral sequence are all mappings of total degree plus or minus 1? Right, depending if we're thinking homologically or co-homologically. We're beginning to assemble these notions to give the expected definition. A spectral sequence of algebras, if for each R, this is a differential bi-graded algebra. And furthermore, the product the product on the R plus 1 page is induced by the product on the rth page by on homology. I see. Oh, so we're saying you could define those products separately, but they just need to be compatible in the sense of homology, at the level of homology, if I'm understanding this correctly. Holy moly. So the product on homology can be expressed as this. Right. Okay. To complete these series of definitions, we need to make precise how a spectral sequence can be used to recover a graded algebra. Sander Lewis was in my comment section pontificating about this, so maybe this will finally make some of those details clear. Why do you say the E2 page? I mean, I guess you're just used to starting on the E2 page. I thought we were supposed to think about starting on the E0 page and then hope that our sequence converges on the E2 page. Maybe this is just a matter of convention, though, right? So suppose F is a filtration of H, a graded algebra with product phi. And the filtration is said to be stable with respect to the product. Right. You're just used to it. The vast majority of spectral sequences in practice, they start on E1 or E2. I thought they would finish on E1 or E2. Ooh, look, we've got an example. A nice, juicy, explicit example coming up. Yay. Yay. Makes me happy. The reader will want to check that a filtration that is stable with respect to a product on H induces... you can't tell me what I'm going to want. Can't tell me that. Sorry, I'm tired. I had to make sure I got up on time so I could do a quick office hour and go. That is stable with respect to a product on H induces a bi-graded algebra structure on the associated bi-graded module. Okay, I haven't woken up enough yet for this. We want to check that a filtration that is stable with respect to H induces a bi-graded algebra structure on the associated bi-graded module. Right. And E double star 0 was the summing over something. Let's go back to our notes here. What did we have? E. What did we have? That was the sum. Right. That's the sum of these quotients. That's if we have P in one component. I think if we have a Q in the second component, we sum over all Q. Something like that. Okay. So, we can now say what it means for a spectral sequence of algebras to converge to H as a graded algebra. That is, there is a spectral sequence of algebras and a stable filtration on H, with the E infinity term of the spectral sequence isomorphic as a bi-graded algebra to the associated bi-graded algebra. Right. Right. Okay. All right, let's jump in. Let's jump into this juicy example. Let us get prepared to do some writing. Get out your notebooks, gang, and draw along with me as we go. No, don't. Okay. So, we're given an E2 page. Hello, Lockheed. So, we're given an E2 page. It's going to be rational polynomials in 3 variables modulo x squared y4 z squared. Incredible. Okay. The bi degree of each generator is given by y. Why is he choosing it that way? We'll never know. And by never, I mean maybe the example will make it clear. Or maybe he was just like, oh, well, here are some funny numbers to work with. That is, yeah, I can't for the life of me see why we would make those choices, but whatever. Suppose furthermore that d2x, what? Oh, that d2x, right, the map d2 applied to x is y cubed, and the map d3 applied to z is y. Then this collapses to E4, and XY is kill, but no XY. No XY kill until the end. Okay. We observe that we only need to know the action of the differentials and the generators of the algebra, since the Leibniz rule tells us how the differentials act on decomposable elements. Do we have the Leibniz rule, though? Do we have... I don't think we were told what happens on Y. Okay. With the given information, we can list the entire E2 term page of the spectral sequence in this diagram. Oh, but we do know about the bi degrees. If we know about the bi degrees, I guess that tells us the total degree. Still yet to catch up on part 4, but has there been an explanation on why spectral sequences start at E2 and not E0 or E1? I don't know. 2's a less lonely number. That's your explanation. Well, today's going to be a short episode, so it'll give you more time to catch up. I see, right. So if we know the bi degree of, so x is bi degree 7, 1. So where is x on here? Right, 1, 2, 3, 4, 5, 6. Yeah, 7, 1. And y has bi degree 3. So, right. So then if you multiply things, you should add bi degrees. So y cubed should have bi degree 9, I guess. And then on the E2 page, if x is in 7, 1, D2 E2 7, 1 should go to E9. Nice. That's what we wanted. 1 minus 2, negative 1 plus 1 is 0. Sick. Tight. Okay. Programmers and mathematicians versus engineers, whether 0 is the starting point or not. And this is a spectral sequence, guys. Yeah. Homotopy theorists at -2? Oh, man. This indexing war is about to get heated up. Now that we got some real wild cards entering the chat. Since the differential d2 as shown takes basis elements to basis elements, yeah, I guess it does. It is clearly an isomorphism of vector spaces when non-zero. We take homology to obtain E3 as this diagram. Yeah, sure. And finally, by the placement of trivial vector spaces as presented in the diagram, this has to be E4. Notice that the product xy has lived to E infinity, even though the generators did not. Furthermore, we can read from the spectral sequence that the element represented by xy times the element represented by that is a non-trivial product. Okay. What? Though the example points out how a spectral sequence simplifies in the presence of a product structure, it is particularly simple with regard to the problem of reconstructing the algebra structure on H. The reader should contrast this with example 1J, in which the E infinity term is shown to be inadequate for the determination of the algebra structure. The sequence can still, in theory, start at E1 or E0, but the theorem already computes for you the first couple of pages. So you start at E2. I don't get that at all. I don't understand what you said in the slightest. Usually computing E3 and beyond is more specific, but E2 can be done in generally. Huh? But yeah, as you say, an abstract spectral sequence can start at page whatever. Yeah. Okay, so we're actually gonna end it there today, I think. Like I said, really short office hour. I got places to be. Actually, let me check something first. We might be able to stay a tiny bit longer. Basically, depending on bus times. I should have done this before stream. Quite short indeed, yeah. Well, let's see. Maybe I can stay a little bit longer. Or maybe not. Is there anything more cool than math? I don't think so. Okay. Well, if I rush, I could maybe get the next bus. Okay, I'm gonna rush.